Hi everyone, myself Subarno and I am going to talk about the foundation of quantum theory in my first lecture. Quantum mechanics is not a rocket science. It's a fundamental part of how our own familiar world works. Perhaps no other area of physics has enjoyed as much attention from scientists and non-scientists as quantum mechanics. The fame of quantum theory lies in the physical weirdness they manifest. Even some of the scientists who discovered those theories got surprised to see its bizarre nature. But in spite of it, it's not that complicated or it's not in that much inaccessible as they might seem. Let's decode this wonderful world together. Before going into the deep, we have to first understand why quantum mechanics was required. In the universe, one distinguishes two categories of objects. One is matter and another is radiation. Matter is made up of perfectly localized particles subject to Newton's law of motion. The state of each particle is defined at any instant by its position and its momentum. On the other hand, radiation obeys Maxwell's law of electromagnetism. Its dynamical variables are components of electric and magnetic fields at each point of space. In contrast to matter, it's not possible to split radiation into particles which can be localized in space and maintain its localized character during their time evolution. Quite to the contrary, it exhibits a wave-like behavior which manifests itself particularly in well-known phenomena of interference and diffraction. So, the particle is a localized concept, whereas the wave or radiation has got delocalized character. The corpuscular theory of matter was able to explain all the macroscopic properties of matter, but the scientists soon realized that it has microscopic or atomic scale origin, and the macroscopic properties appear as the mean values of certain dynamical variables of a system having very large number of degrees of freedom. As for example, pressure arises if the large number of gas molecules hitting to the wall of the container. So pressure is the average property and its origin is its microscopic origin is the large number of molecules is hitting the wall. As the large number of degrees of freedoms are involved here, so there is no hope of solving this kind of problem exactly. And the statistical method of investigations was required. Thus a new discipline originated and developed. It's called statistical mechanics. Statistical mechanics, along with thermodynamics, enables us to verify the foundation of classical theory of matter. So, toward the end of 19th century, the success of classical program was impressive. All known physical phenomena, it seemed, find their explanation in a general theory of matter and radiation. And some thought around that time was physical science was approaching completeness, at least theoretically, and the only left part was make it more precise and apply it in different disciplines. But towards the end of 19th century, physicists could not get explanation of some phenomena whose origin is microscopic in nature. These phenomena are black body radiation, photoelectric effect, atomic line spectrum, and heat capacity. We are all familiar with the different components of a candle flame, or the way the metallic rod goes from faint red to bright red as temperature rises. If we could increase the temperature even higher, we'd eventually see the color of metallic rod is shifting from its reddish glow to more of a bluish hue. In essence, what we are observing is a very specific relationship between the temperature of a hot object and the light it gives off. As the temperature increases, the light emitted from the metallic rod shifts to a higher frequency, and although our eyes only see a particular color, it's actually a range of colors or a frequency spectrum that's emitted. This seemingly mundane physical phenomenon shocked the entire physics community in the 20th century, and they were out of explanation. And it would ultimately provide the very first peek into the bizarre world of quantum mechanics. When radiation falls on the surface of a body, some is reflected and some is absorbed. A black body is defined as a body which absorbs all the radiant energy falling upon it. In other words, its absorption coefficient is equal to unity at all wavelengths. Thermal radiation absorbed or emitted by a black body is called black body radiation and is of special importance. In the left side, we are seeing a picture which is a good approximation to a black body. Here, a cavity is kept at a constant temperature and having blackened interior walls which is connected to the outside by a small hole. To an outside observer, this small hole appears like a black body surface because any radiation incident from the outside on the hole will be almost completely absorbed after multiple reflection on the interior surface of the cavity. Because the cavity is in thermal equilibrium, the radiation inside it can be closely identified with the black. A perfect black body is of course an idealization. It can be very closely approximated by a hollow box with its blackened interior with a small hole. The black body absorbs and re-emits all the incident light in it, and we can analyze this spectrum or the light that is coming out by prism spectrophotometer just in the similar way what Newton did. It's for the white light. So when white light passes through the prism, its component lights are coming out. This similar thing we can apply for the black body radiation to analyze it, and it is expected that it should be well explained by thermodynamics and electromagnetism. But there are many surprises left. Let's see what are these experimental features and what are the classical prediction regarding regarding the analysis of this black body radiation. When we analyze the radiation emitted by the black body, which is there in the right hand side of this slide, we got two interesting features. Number one, the intensity of blackbody radiation shifts to lower wavelength as temperature increases. If we see this plot carefully, you will see at 5000 Kelvin, the, the light emitted by the blackbody is blue in nature, and at 3000 Kelvin, it is reddish in nature, which justifies what we have told earlier in case of hot metallic rod or from a Bunsen burner. The second most interesting thing uh, interesting feature of blackbody radiation is initially with increasing the wavelength, intensity of blackbody radiation increases. Then it reaches a maximum and ultimately falls down at very high wavelength region. According to the classical theory, it could only explain this feature at very high wavelength, which is depicted in this black curve of this plot. This classical theory fails drastically in the shorter wavelength region, which is called ultraviolet catastrophe. I will explain I will explain it with more mathematics and with detailed expression in the upcoming presentation. But right now I am only giving you the overview. Max Planck was able to observe. German scientist Max Planck was able to explain the blackbody radiation by considering the fact that the interaction between radiation and matter that results in the frequency spectrum, the matter can only absorbs and emits energy in specific amounts, which is E equal to h nu, where h is the Planck's constant and nu is the frequency of incident radiation. In other words, the energy values allowed are discrete rather than a continuous distribution. So if an atom's energy goes up or down, it must do so in specific increments, no more, no less. Let me give you an analogy. Imagine an empty bucket. Outside the bucket, there are two objects. One is water and another is balls. Another is tennis ball. Now, this balls or water represents energy and the box represents matter. Now, according to classical mechanics, matter can absorb energy in any amount. So, we are free to place water in any amount until it's completely full. It's a continuous distribution, which is analogous to the situation that energy is continuous. However, according to quantum mechanics, energy can only be absorbed in specific increments. Therefore, I am restricted to use a specific number of tennis balls here, and the box can only be filled with this energy quantum, which represents the discrete nature of the energy levels. Now come to the another experimental phenomena called photoelectric effect, which forces a radical revision of the radiation theory of Maxwell. Photoelectric effect means the emission of electrons when it is the metal irradiated when the alkali metal irradiated with the UV light under vacuum condition, and as a result we get a photocurrent. However, for a given metal there is a certain cutoff frequency above which the knocking out of electron occurs. Although the magnitude of photocurrent is directly proportional to the intensity of the incident light, early investigators were puzzled to discover that the maximum kinetic energy of the emitted electrons depends only on the frequency and was completely independent of the light intensity, according to the classical theory of light. So, the classical theory predicts that the radiant energy should be distributed continuously and uniformly over the entire wavefront. So, the ejection of the photoelectron should depend on sufficient intensity and not on the frequency. But the experimental observation tells the difference. Since the photocurrent begins virtually instantaneously upon illumination, there appears to be insufficient time for the electron to accumulate enough energy from a uniform wave source. So, there should be a time lag between photoelectron emission after the light rays fall into it. But in experimentally, we uh, observe that photoelectron ejects instantaneously after light rays shines on the metal surface. So these are these theoretical prediction by classical theory and experimental uh, observations that is given in this tabular form. In 1905, Albert Einstein suggested an extension of Planck's quantum idea which accounted for the detailed understanding of photoelectric effect. Einstein postulated that light or radiation consists of consists of particle or quanta, which is called photons, with an energy equal to h nu, where h is the Planck's constant and nu is the frequency. This is just the energy units which a black body absorbs or emits. These photon energy h nu would be used to overcome the attraction of the electron to the bulk of the metal, and if any energy were left over, it is imported as the kinetic energy of the free electron. This is mathematically expressed as h nu equal to half m Vmax square plus phi, where Vmax is the maximum velocity of the ejected electron. This phi is called work function of the metal. The work function is the minimum work needed to remove an electron from the metal. Einstein model further implies that the work function is related to the threshold frequency nu 0 by phi equal to h into nu 0. Let us understand this photoelectric effect by a common analogy. Imagine there are three items. One is some bricks which are arranged over one another. Second thing is a table tennis ball which has very low mass, and another thing is a heavy shot put ball which is a heavy object. Now the arranged bricks represent an electron sitting in the outer shell of the metal atom. If we now throw a table tennis ball onto the bricks, it would not the bricks would not fall over. Even if we throw thousands of TT balls, the bricks would not fall over. The ball does not have enough energy to knock the electron, or bricks cannot knock the electrons out. So no matter how much intensity of the light is, electron will not be knocked out. If we now throw it with a heavy shot put ball with more than required energy, the bricks will not only fall down, its excess energy of the ball will be imported as the kinetic energy of the bricks, and we'll see the disruption of this structure. This photoelectric effect breaks the previous understanding of the wave nature of the radiation and introduce the particle aspects of light, which is again surprising. The third interesting phenomena leading to bizarre nature of quantum mechanics is the problem of atomic line spectrum. The spectrum we observed are mainly of two kinds. One is continuous and another is discrete or line spectrum. In continuous spectrum, the light source that is shown in the left side of this figure, a white lamp, emits all wavelength of visible light. When the light is passed through a prism, the different wavelengths are separated and we see a spectrum of rainbow colors from red to violet. On the other hand, when light comes from an electrically discharged gaseous element passed through the prism, which is there in the right side of this figure, the spectrum with big gaps, and it's not a continuous one. It's called a line spectrum. The line emission spectrum of an element is a fingerprint of that element and can be used to identify that particular element. The chemists usually do it by doing this flame test in the laboratory to identify the element. Uh, uh, to identify the element by its characteristic color. As we see in this figure, this sodium is golden yellow and potassium is lilac and so on. The case of hydrogen deserves a special mention here since it's the simplest of all atoms. All the observed frequencies of hydrogen atoms obey empirical formula R of 1 by Na square minus 1 by Nb square, where Na and Nb are integer and the value of Nb is greater than Na, and R is called Rydberg constant. Experimental facts are in clear-cut disagreement with the classical radiation theory of Rutherford atom. According to the classical theory, as electron in atom carry a periodic motion, the emission frequency would be integral multiple of some fundamental frequency. But even for hydrogen atom, it fails to explain the observed nature. Along with that, Rutherford model itself encountered a serious challenge as it cannot explain the stability of atoms. This is due to as electron is charged particle, when it orbits a nucleus, it emits electromagnetic radiation and eventually electron should fall onto the nucleus, which leads to the collapse of the atoms. In 1913, Bohr gives the explanation that the atom does not behaves as a classical system capable of exchanging energy in a continuous manner. It can only exist in a certain number of stationary states, each having a well-defined energy. These postulates allow us to specify the mechanism of absorption or emission of light through quanta. In presence of light, an atom can undergo transition to a state of higher energy by absorbing a photon of energy h nu. Similarly, an atom can undergo transition of a state of lower energy by emitting a photon of energy equal to h nu. In this discussion, we have analyzed the main difficulties encountered by classical theory in the domain of microscopic physics. It is assumed that position and momentum of a particle can be determined simultaneously with arbitrary precision. This is only true for the macroscopic or bulk object. In such cases, classical mechanics can be used safely and these objects are called classical objects. If you see this curve in the left side of the slide, this P and Q, P is position and P is momentum and Q is positions. So if you see this plot, you will see the evolution of this particle or the classical particle can be measured at any time instant. The space spanned by this P and Q is called phase space. So here for classical particle, this phase space trajectory is sharp. But for microscopic objects or subatomic particles, the situation is quite different. For this object, there is an intrinsic principle called Heisenberg's uncertainty principle, which states that position and momentum of an object cannot be determined simultaneously with arbitrary precision. Due to this uncertainty, classical mechanics cannot be applied for microscopic or subatomic particles. If you see the right side plot of this slide, you will see that here there is no concept of phase space trajectory, or phase space trajectory is not to. If you look at the right side plot in this slide, you will find that there is no phase point exist. Rather, this phase point is replaced by an area element. All this is arises due to this uncertainty principle, which tells that position you cannot simultaneously measure position and momentum of a particle with arbitrary precision. So higher the certainty in measuring this position, more uncertain is the momentum, or vice versa. Okay. Another thing that also leads to the failure of classical mechanics is the nature of this radiation. As we have pointed out, that radiation has got corpuscular nature along with its wave nature, explained by Einstein. So what is the way out? The way out is we have to develop a new mathematical tool which can be used to understand the statics and dynamics of subatomic particles, and these mathematical tools are quantum. So we have realized that all is not well with the classical mechanics to understand our nature, which eventually gave birth to the new mechanics called quantum mechanics. Now I will tell you briefly the progress of knowledge in quantum mechanics which occurred in 20th century. At 900, Max Planck resolved the long-lasted problem of blackbody energy distribution and introduced the concept of quantum or discrete nature of energy, which I explained in towards my first slides. At 1905, Einstein explained the photoelectric effect and introduced the photon concept of light. At 1912, Einstein explained the temperature variation of heat capacity of solid, and it is modified by Debye in the same year. At 1913, Bohr explained the line spectra of hydrogen atom or hydrogen-like system. 1914 to 1916, Wilson and Sommerfeld gave a general principle to get the quantized energy expression for a series of problems popularly known as Wilson-Sommerfeld quantization rule, which we will present in the next time. This is often called this old quantum theory. At 1918, Bohr gives Bohr's correspondence principle, or this classical quantum correspondence principle. At 1921 to 1922, Stern-Gerlach experiments gives the idea of quantization of space and gives the idea of spin quantum number. At 1923, Arthur Compton gives the Compton effect. At 1921 to 1922, Stern-Gerlach introduced the concept of electronic spin, and eventually the idea of spin quantum number comes. At 1923, Arthur Compton tells that light also carries momentum, which validates the Einstein's theory of corpuscular nature of the light. In 1924, de Broglie gives famous wave-particle duality, which tells that if light can carry momentum, which is the characteristics of particle, then all moving particle can carry wavelength. At 1925, Heisenberg gives famous uncertainty principle, which we have discussed a bit. At 1926, Schrödinger gives the Schrödinger equation, which is the heart of the quantum mechanics. And 1927, Dirac developed relativistic Schrödinger equation called the Dirac equation. So thanks for your patience. I hope you enjoyed my lecture.